Hello students, welcome to the second lecture in the module Numerical Methods for Engineers. In this lecture we are going to look at something which is slightly different to what we saw in the first chapter, right? In this chapter we will be looking at integration. Numerical integration is normally referred to as numeric quadrature. Okay, so when we talk of quadrature, just remember that we are talking about numerical integration. Okay, now the starting point is the problem which we want to solve in this chapter. Okay, so the problem is to integrate f between a and b, right? Now what happens in most cases is that you may not be able to integrate exactly, okay, because maybe the f is very difficult to integrate. Okay, so in that case you need to approximate it. Okay, and when you approximate an integral, that is what's referred to as quadrature. All right, so all quadrature methods take the form like this. Okay, so it's basically a sum of the f, so the sum of the f's which are weighted, right? And you by now you know that each time you approximate something by an approximation, there will be an error that results. All right, so the error is basically the exact here minus the approximation, right? So instead of doing the integral, we are going to replace it by a summation of the weighted f's, which is what you see in 3. All right, you can also do quadrature by replacing the f by a polynomial of degree n. All right, and the reason why you want to do this is that polynomials are easier to integrate exactly. All right, so all these are also methods of quadrature. Right, now the first method I want to talk about is called the trapezoidal rule. All right, so the trapezoidal rule works as follows. So we are trying to integrate between a and b. What we simply do is to divide that interval a to b into n equal parts, okay, which is what you see here. Okay, and then to find the integral of f, which is basically the area under the curve, the blue curve here, we will then approximate it by taking the sum of these trapeziums. Okay, the sum of these trapeziums. So when you add up the sum of these trapeziums, then you will have an approximation for the area under the curve. All right, so that is how the trapezoidal method works. Okay, so it's basically a sum of these small trapeziums. Okay, now let us see how it works. So like I said, we're going to divide a to b into n sub intervals of equal length. When you do that, it means that you are going to have n plus 1 points. All right, so these are from x0 to xn. That makes it n plus 1 points. Your starting point is x0 and your end point is xn, which is b. All right, now the difference between your x's, which is what we see here, is the h. Remember, this is what we also saw with numerical differentiation. The difference between your x's is h. So in other words, how you move from one x to the next is by adding h, and this h is simply the b minus a over n, right? So the size of each of the n subintervals. Right, now each subinterval we are going to approximate the f by a first degree polynomial, in other words a straight line. This is what we saw from the diagram. Between each of the x's, between this and that, we are going to put a straight line between this and that, we're going to put a straight line. That is the first degree polynomial, basically a straight line through those points, right? Now if you draw a straight line between this point and that, then the straight line will be of this form. All right, so you need to verify this. All right, make sure you can draw a straight line between xi and rather f at xi and f at xi plus 1, right, which are these f's. All right, so when you draw a straight line between those points, this point and that, this point and that, you are going to find that it is of this form. As you can see, it's a first degree polynomial. The highest power of x in this expression is 1, right? Now once you have that straight line there between each of the 2 points, then you find the area under those 2 points. Okay, under those 2 points, so we are finding the area between this and that, the area of this trapezium. Okay, now when you do that, it means you are going to integrate the p1 like this. Okay, you integrate that. There are many constants there that you can take out of the integral. If you do it right, you're going to find this. Okay, so this is basically the area under the trapezium, the area under these 2 points. It's a trapezium, as you can see, and from high school you know that the area under this trapezium is half of the 2 heights. You add that up and then you multiply by the distance between the axes, which is h. Okay, so when you do that, you're going to get this. So even if you do not, even if you are not able to find this expression, just remember that here we are trying to find the area and the area of a trapezium. This is the area of a trapezium, and it is given by this. Okay, you can do this. It is very simple. All right, now once you have been able to find that, the total area between A and B, the total area between A and B is going to be the sum of the areas of these trapeziums. So 1, 2, 3 up to n. All right, so the total area is going to be the sum of the trapeziums. Okay, this is what we are basically doing here. And then if you simplify this, collect terms together, this is what you will find. Okay, and this is known as the composite trapezoidal rule. It is the quadrature rule, in other words, an approximation of the integral of f between a and b. Okay, the 2 here is because all the inner sides are used 2 times when you take the areas. What do I mean by that? It means when you find this area, you're going to use this height. Okay, and when you find this area, you're also going to use this height. Okay, so all the heights between A and B, all the ones inside, are going to be used twice. Once to find this area, and then once again to find this area. So that is why you have that 2 there for all the inner axes. All right, so that's the rule. Very simple to do. You can do it easily. It's not very difficult. So this is the f at x0, this is the f at x1, this is the f at x2, and so forth. All right, now the error that you make by doing the trapezoidal rule, in other words, the error that you make by approximating this by that, can be shown to be this. Okay, so remember, the area is always between the error is always the difference between the exact and the approximation. Okay, so our approximation here is a sum, and it can be shown that this is the case. Okay, for those who would want to find out, you can read about why this is the case, but we are going to skip all those details. But I expect you to know its general form. Okay, the general form of the error that you make. Okay, as you can see here again, you can see that it is a second order method. As you can see here, if you take an epsilon between a and b and use it here, then you can see that this term here is h squared, so that means it's a second order method. Okay, so let's look at an example. So here's an example. We want to integrate this between 0 and 1. We are going to take n to be equal to 6. That means our x's will be 7. We have 7 x's. Okay, now once we have n, we can immediately write the h. Remember, it is what? B minus a over n. So we do that here, you get 1 over 6. Now you use your formula. The formula, how far should we go in terms of the f's? So we have f0 all the way up to f6 here. And that's exactly what we have. We multiply by half of the h here. This is the formula we have, and then we can sum. Okay, so to find f0, that would be f at x naught. Okay, x naught is a, and a is 0 here, so f at x naught is going to be 1 over 1 plus 0, that's 1. Okay, now x1 is going to be found by this. So this is how we can find our x's. This method works in general. Okay, so x naught is x naught, as you can see. X1 is x naught plus 1h, so that's x naught plus h. X naught is 0, so that's 0 plus h. 0 plus 1 over 6, so x1 is going to be 1 over 6. So f at 1 is going to be 1 over 1 plus 1 over 6 squared. Okay, that is what you put here. You simplify all these, this is what you get. Okay, always use this as a way to find your x's. Okay, once you have your x, you can now substitute for f here. Okay, the f is this. All right, now the exact value of this integral is pi over 4. Okay, pi over 4 in your calculator will be this. Okay, and if you compare our approximate and the exact, you will see that we are correct to 2 decimal places. Okay, 7878. Okay, 2 decimal places, and it is not very bad. We can always improve on that, but that's a very good starting point. We got 2 decimal places right. That's okay for now. All right, so I'm going to stop the video. In the next video, I'll be talking about the next method.